Could you hear me now?
Yes.
Yes.
Okay, perfect. Thank you. Okay. So the kinds of problems that I wanted to solve today will be, and I will put them, I will upload them on whether we can solve all of them or not, but I will upload them on eCampus. So let me see here. Okay, let's assume that we have a load, which is.
I have a question.
Yes, go ahead.
In the Sunday review, we derived the Z matrix. So for the exam, can we just use the table immediately instead of?
Oh yeah, yes, of course. I mean, if I want you, if I say, yeah, if you have especially if it's from a book, you can write it directly. If I say derive it, if I want you to derive something, I will say derive it.
Okay, sounds good.
Yeah. Okay. So let's assume that we have a load here, ZL equals 100 ohms, and on that end, I have a source and I have an impedance here for the source, ZS. And then I want to put a network in between. That is going to match the load to the source for maximum available power delivered to the load. Okay, so I could probably say, that I would like you to find the matching network. So that's what I could articulate it. Find the matching network here. So maximum power gets delivered to the load. To ZL. And assume at this point that Z sub S is 50 plus J 35. I could give you something else. Let me make it different. Plus J 120. Okay. What are the things that we will have? Number one to consider. To be able to have maximum power delivered. Let me admit this student. All right. Then I would, what we have to make the input impedance here. How much should this be?
It should
What
be
do you
the
think?
conjugate of
Yes.
ZS, so 50
Yes.
minus J1.
Yes. ZS complex conjugate, all right? Which means it has to be 50 minus J120. Now, also we know that whatever we do, it will be nice to normalize things. So we have smaller values to deal with. And I would always do that. So I would, especially when you start looking at matching networks, I will say, whether I'm asking you to do this or not, I will say, and then I will use a reference load of Z naught, which is 50 ohms. There's nothing you will lose by doing that, whether I'm asking for it or not. Okay, so here. So when you do that, then everything gets normalized to this, which means your ZL normalized will be 2, and your ZS normalized will be 1 plus J, what is it? 2.4. All right, so practically, we will have to find a Z in normalized, which is going to be 1 minus J, 2.4. Okay, my preference is to use the Smith chart. How would you do it? Can I ask those of you who are connected? How would you go about doing this? What method would you use? Let me ask you, each one of you. Could you tell me?
Just to be clear, in this scenario, we're making a matching network out of transmission lines where the characteristic impedance is fixed, right? So
Yeah, 50 ohms
okay.
said, is it not?
Okay, right.
How would you, yeah, tell me.
I would probably use either an open circuited stub or short circuited stub, depending on how we're like realizing the circuit.
Yeah, before we go to the design, how you specifically materialize it, what kind of tool are you going to use to get there? That's what I'm asking.
We'd go about finding the reflection coefficient and then VSWR.
Yeah, no, tool. Are you going to use MATLAB? Are you going to use something else? Are you going to use the Smith chart? Are you going to use analytic models? What are you going to use? What each one of you uses when you try to solve these kinds of problems?
I think probably the chart.
I could not hear.
I think the easier way is to use a Smith chart.
For those who have, yes, the Smith chart. Others? How would you be able to solve this problem? What kind of tool would you use? I'm asking so I can modify my approach accordingly.
I'd use the Smith chart probably.
Smith chart too. Anybody else?
I've tried using MATLAB before with very limited success. I would definitely use a Smith chart too. Yeah.
Can I ask you, does MATLAB allow you to do the design or you just do analysis?
I mean, when I did it, I had essentially to plug in all the equations.
Yeah.
And then just kind of graph them and see like where they intersect to find the links to the lines. But that actually ended up not working at all, probably because I messed up one little piece of the algebra you had to do to get there. So
yeah,
it's kind of a tricky thing to do in my opinion.
The Smith chart is the easiest if you guys can use it, but in case you can't, I understand, So the other thing that I would do is if you have a PDF of a Smith chart, you can import it on a PowerPoint and you can use circles using the PowerPoint tools to be able to find an initial at least solution. And then you go to MATLAB and you confirm it if you have access to MATLAB. That's what I was thinking. It's possible, all right? I was doing that for some time and it's decent. I'm not suggesting, because you can do straight lines, you can do circles on PowerPoint. But in any case, for those who have access to the MATLAB, PowerPoint is the easiest way to do it. And I will, in this case, bring a PowerPoint, Smith chart.
Dr. Kategi?
Yes.
Sorry, I had to step out. I had to let someone into my.
Yes.
What were you saying about MATLAB and the?
So
Smith
what I was saying the following is MATLAB. I don't think MATLAB not having used MATLAB for a long time. I don't know. Does it do designs? That's what I was asking. And
Oh,
one of
I could share my screen and show you what the code that I have.
okay, let me see. Let me
Okay.
allow you to do that. Just a second. Okay, let me see what you have.
Okay. Let me pull it up. It's basically just all the equations for the analytics. So I'll share my screen here. So can you see it?
Yes, I can.
So I just put the S parameters in, calculate D and K. I got the B's. I just plugged all the equations in. Here's gamma.
Oh, that is for the, that's for the matching network. Okay.
And then once I actually go through and I want to design, I solve for I call it the target impedance by rearranging the equation. And I turn that to a target admittance. I get a quarter wave transformer equivalent impedance or characteristic impedance. And then I also get the stub length. And then that tells me pretty much what I need to know for the design. So it'll give me the length of the shorted stub.
So it does that. Okay.
Yeah, and it's just plugging in the math. That's there's no
that's fine.
preset design stuff.
Okay, that's fine.
I was gonna say
that's good. Yeah.
Like it seems like what Ryan did and like what I use Mathematica to do is you do have to assume like a form of what your matching network's going to be. So you have to like say that you're going to use an open stub and stuff like that, and then plug in those equations and then solve. But it works just fine.
Okay, that sounds good. So I'm going to use the Smith chart because that's the most visual and it's easy for now. But for those of you in the exam, if you can use MATLAB, if you are familiar with that enough, so you can do it fast and everything, do that. All right. I'm not gonna specify in the exam or in any other part of this work that we have to do for this class how to do it.
Great, thank you.
For now, I'm gonna use the Smith chart myself. So I'm old school. I was thinking the other day, it's very hard to teach an old dog new tricks. So while I've learned MATLAB, I always like the Smith chart. So, but in any case, most of my colleagues do the same. We are all very old people. But in any way, I took the normalized quantities. Here we normalize with respect to 50 ohms. And then in this case, we want to do a conjugate matching, obviously. We are looking at the load, and the load here is going to be at 2.
Professor, we can't see your screen.
Because I gave it up. Yeah, thank you. Hopefully you'll see it now.
Yes.
Okay, so ZL is a 2. And then whatever you do after that, you will need to, there are 2 ways to do it. All right. Personally, I don't like, if I have to use a stub, I don't like to use it immediately at the load because you never know what your load is. And then attaching something right where the load is not very good. You need to give your time because here is what's happening. Especially if you are in hybrid, not in fully integrated circuits where everything is fabricated. You just create a layout and then it goes all automatically. A lot of times when you work in lower frequencies, you just put chips together, all right? You have like a semi monolithic, so it's hybrid integration as we call it. So you take different chips, you put them together. So if your load is a different chip, then usually the way you connect them depends on the frequency. If you're at lower frequency, you can do just a bonding wire. So you go from the output of one to the input of the other. And I don't necessarily like to use stubs very close to that because it messes up a little bit your circuit. So I would always start with the transmission line and then place the stub a little later, if I may, as opposed to starting with the stub. That's why I always personally start moving around the constant VSWR circle. And because there are two ways. In fact, we want to go from A, which is from, let's call that B. All right, let's assume that this is our load, B. And we want to go to A, which is the complex conjugate of the Z sub S. And the complex conjugate of Z sub S is 1 minus J 2.4. So it's going to be 1 real part here. So 1. We move from 1 until we see 2.4. 2.4. Well, it came like a straight line. That's all right. So, okay, so 2.4 is going to be here. So practically, the point where I want to go is right here. 2.4. And I want to make sure that it's the complex conjugate. Yeah, put part. Okay. So I'm going to go from B to A. How many ways can I go to go from B to A? Let's think about that. One way is to start moving on a transmission line from B away from the load, which means I will have to move along the constant VSWR circle that goes through B. And then at some point I will have to put a stub. If I put a stub immediately, which I would not suggest, then I will have to walk around the resistive part equal to circle away from where the point B. And then I move until I find the constant VSWR circle that goes away. Is that clear, or was it confusing?
Show us what you mean on the diagram.
Okay, so I will do two different things. The first approach is to work on to move around a constant VSWR circle, which implies that I'm moving along a transmission line. So I'm going to draw a constant VSWR circle that goes around this point B. Okay, so let's move that. Just a second, let me just try. There. Okay, this red circle is the constant VSWR circle that goes through B, which also implies that wherever you go along this circle, it's like you move along a transmission line. If you go from, because B is the load, if you go from the load towards the generator, that you will go along this way. All right, that's towards the generator. So from B, I can go clockwise, and wherever I go, that implies that I'm going along a transmission line. If I take that route, then obviously I will stop at the point that is going to get me the closest to A, but on a constant resistance circle. All right, so practically, if I go like that, I will go here like this from B to this point, which shares the same resistive part with A. So I went from B to say C, an intermediate point. And so that says from B to C, I moved along a transmission line. And now to be able to go from C to A, I have to move along the constant resistance circle like this. And if I move like that, I have to make my negative reactance that corresponds to B more negative, which means I will have to add in series a capacitor. All right, that's how you make something more negative. And when I go from B to A, I change only my reactance. So practically, it's like having the following. It's like I am here with a load. Okay, that's my load, normalized, and that's point B. And then I move along the constant VSWR circle until I go to point C. And at point C, I add a stub, like the green one. And the stub I add it gets me to point A. So this one has to be a minus JX. All right, so at C point, my impedance right here is equal to 1 minus J.7. So it's equal, normalized, to 1 minus J.7. And to be able to go to A, where Z sub A prime is 1 minus J 2.6, I need to add more reactance, to put more negative reactance. So practically, I need to add the stub that gives me a minus JX, which is equal to minus J. The difference is like 1.9. Okay? So that is one way of doing it. So what is a negative reactance? So practically it's like I'm adding a series capacitor, all right, between C and A. That's one way of doing it. The other way, I'll use different colors, is to go to draw the constant VSWR circle through A. That shows me if I were to connect from A towards B, a transmission line, it would go through this A point and it will be okay, let's see. Something like that, a little lower. Okay, something like this, I think. There, perfect. Okay, so the purple circle is if I were to add a transmission line next to the source, all right, from the front part of this. If A is here, and this is B, C is somewhere in here. Somewhere is C. Now, there are two options. Either I'm doing the first option where I move along a transmission line after the load. Okay, here. And then I put a series stub here that gives a capacitive load. Or if I don't want to do that, I remove this and this and this. And then I draw I use a transmission line from here to here. And then I put between these points a stub. And I want to see what kind of impedance this stub is going to give. All right, but so I do it like that. Okay. If I go down there, therefore, I would have to move from point B somewhere on the purple circle. To do that, the only way I can go from B to purple is by moving along the constant resistive circle. If I move along the constant resistive circle by this, then I need to move going towards the generator, goes like that. So from there, I will move like that and come to A. So either I follow the purple line with these arrows, or I will follow this one first, and then the green, and I'm getting to the same point, which is A. We did the first one, and we found what we need to get. Let's do the second one. The second one implies that I will have the load here, that I will put a series stub, and then from here, I will put a transmission line. All right, so I'm here, ZL, and then I put a stub and then transmission line. And then the stub I have to put, I need to move from this point here, this point, whose reactance is somewhere here, and it's minus 3.2. This point here is minus 3.2, normalized. I have to move to point A. Excuse me, no. I have to move from the reactance of B, which is 0 here, red, to the reactance of this point C, which is right here. So, and as a matter of fact, I have to go from B, which is in resistive part, is 0, to this point here, which is minus 3.2. So I will have to add a reactive part that gives me minus J 3.2, put it here, and then move on a transmission line by this amount until I go from C to A. And this is the dimension. This is the distance that will give me the dimension of the transmission line here. So there are two possible solutions, as you can see. I don't know, I don't care which one you're gonna, of the two you're gonna identify. Either one is fine with me. So usually I always go on a VSWR circle. I usually follow the first solution. Depends, I mean, at this point, without any other constraints about what kind of solutions we can consider, either one of the two is fine. But I was going to use the first one. Any questions so far?
Yeah, Professor, I had one question.
Yes.
In the second option you do the transmission line to the left, but on the first one, it would be between C and B, right? Under the Smith chart?
In the first one, you move from B to C.
Oh, scroll down. On the transmission lines that you drew and
yeah.
On where you were doing the math and where
yes.
where you drew the I guess schematic.
Yeah.
In between B and C is where the transmission would be on for the first.
Yes.
Okay.
Yes.
I just wanted to double check because you didn't draw it.
Yeah. Between B and C, the transmission line, whenever you see these concentric circles, the red and the purple, they show transmission lines. From B to C, that's where the transmission line is. From C to A, that's where the transmission line is. In the first one, you go on a transmission line, then you put your stub. In the second one, you put your stub first, which is from B to C, and then your transmission line. Either one is fine. I mean, if you don't have other constraints. Okay, let's do the first one for a moment. You could follow the same thing for the second one, but let's do the first one just so we can, we're not going to repeat the other. The approach is going to be the same. So let me erase the second part. Is it okay if I erase the second part so we don't have too many lines there? There. Okay, so that is B. Okay, thank God for that. B. Okay. Point A is down here. Now, what I have is a transmission line. So let me now develop the circuit that I have, which is my load here is Isabel. And then I put a section of the line. And then I put a stub. Which is reactive. So practically what I have, a negative. So what I have here, if you think about it, I have the equivalent of a capacitor in series with a section of a line. And for my design frequency, where this is my length, I will find out, for example, from here, that the length of my line that I have to draw is going to be between here, that point, and I will connect the center of the chart to C. That is not. Okay, this one. And I will measure the distances. So from here is 0.25 if I go to the outer, and this is 0.347. So it's 0.347 minus 0.25. And that is going to give me 7, 9, 30 lambda. So I have a section of a line here, which is 0.094 lambda. And then I have a minus J 1 over omega C, which is, as we said, normalized 1.9. And if I normalize this one, and this one is minus J, so normalized will imply minus J 1 over omega C Z naught. Okay, so I have now a capacitor I can find. So for example, 1 over omega C Z naught equals to, what did we find? 1.9. We took away the minus, all right, the J, so it's 1.9.
Professor?
Yes.
Real quick, it's actually 1.7. It's not that important, but it was 2.4.
Okay.
6.
Okay, let me correct it, thank you.
And above it, it's 2.4, not 2.6.
Ah, okay. It's 2.4. How did I get 2.6 in translation?
I think you just wrote it down wrong, but yeah, it's 2.4.
I always do that. Yes, you're right. Wrong in translation. So 1 point, what do we say, 1 point? And that was 1 point, tell me, 7 for 7. Okay. So that was 7. And then from there, I can find C if I know F, and of course Z naught, I know 50. All right, so I find C. Let's assume that I find C. It's, I want to find it. It's 1 over 2 pi F. Let's assume that F is 10 gigahertz. So that's going to be 10 to the 10 times 50. And that's going to be about 10 to the 12th pi. And that's going to be 10 to minus 12. And then how much is 1 over pi? It's 0.3 something. So 1 over pi. Let's see.
Again, how you get 1.7?
From 2.4, you subtract 2.4, you subtract 0.7, you get 1.7.
Thank you.
Okay. So it's 1 divided by pi, like upon 0.32. So it's 1/0.32, which in fact, so that gives me a capacitance, and inverse this. It's inverse. It's 3.1, 10 to minus 12, which is 3.1 picofarads. Okay, so now I have that, and I have a distance 0.094. So now what you have given me is a capacitance in series with the transmission line, 50 ohms, but I have its length. That's my matching network. Okay, and now what I want you to do is to find its ABCD matrix. So I put that in a square. Okay, so if I go on top and I see, so my AA prime is there, BB prime, so I put that in a square and I have my A prime here, B prime there, and that's my matching network. And now the next thing that I'm asking you is to find the ABCD matrix of that, or. So I can ask you two things. Either one of the two. Either find ABCD matrix of that, or find the Z matrix of that. Or I could say 3, find an equivalent circuit for this. Let's discuss the 3 separate questions, all right, for the matching network. Now, how would you, let's assume that I'm asking you the first one. How would you go about doing number 1? How would we do that?
You could break up break it up into separate things that fit that table from the textbook, and then okay, or you could find an equivalent impedance for the transmission line and add it with the capacitor, and then just find that the one from the textbook that just has like an impedance and do it from there. Okay,
let's talk a little bit about that. How would you find? Of course, we're going to split it, all right, because we know that the book has some simple tables, and we like to take advantage of it. So let's try to split it. Let's assume that we're going to take.
Professor?
Yes.
I think your C value is actually wrong. I could be wrong, but I don't think you divided 1.7 by your original. I don't know. I don't know.
I missed 1.7.
Yeah, I think divided that.
Okay. Let me see. See, yes, I did not divide by 1.7. You're right.
I guess you don't divide by 1.7, but.
No, you do.
Okay.
Because you have to move C up, move 1.7 down, and then you have, yes, you need to have 1.7. You're correct. And so practically I need to have 1.7 here, and then I need to divide by 1.7, this 1.7, this 1.7. Okay, good. And it's 3.1 divided by 1.7. It's 1.82 picofarads. All right. Then we would have to in this one, assuming that we have C, which is here, we need to find either one. Now, we solve for number one. We said that we are going to divide it into two pieces, which is true. The two pieces will be this one, and then piece two is going to be this one. All right. If I do this, then practically what I have is I have one capacitor like this as one part of the network connected with a transmission line like this. It's a second network. So the only thing that I have to do is to find the ABCD matrices of that, of those two, and then multiply. Do you agree? C, here D, Z naught. And then if you go to your book, practically it has, where's the book here? It has the ABCD matrices. Okay, for the first one, which is a capacitor, so if we call this Mn1, and this is Mn2. For Mn1, what do you have? You have your Z, because obviously what the book has is this one. And then what it has for this is the A is 1, B is Z, C is 0, D is 1. So how much is Z? 1 over J omega C. All right? So practically Z will be minus J 1 over omega C. And omega C was 1.7 times Z naught. So you see from here? So 1 over omega C was 1.7 times Z naught, which is 1.7 here. 1.7 times 50. So practically yes.
Can you
Yes.
explain how you decided A, B, C, and D? Like why is A1, why is B, C?
From the book. If you look at the book, on the front, on the last page, they have the ABCD matrices of the like 1, 2, 3, 4, 5, 6 very fundamental circuits.
Which chapter?
Is they have it in the front of the book. Which edition do you have?
The one from 2012. Hold on, I need to.
Okay, I have an older one. Okay.
The 4th edition.
I have a much older one. So I have edition 3, but they should be, look at the front part of the book. And either that or the one that talks about matrices is chapter. I'll tell you what chapter is.
Chapter 4, it's page 190 in the 4th edition.
Thank you. Yes. You see those? So I look at one circuit, the top one. And Z is an impedance, so it has to be 1 over J omega C. So this one then is going to give us minus J no, this one 85. Am I correct? That's what it gives. Okay. That's for one network. Now, number 2 network is a transmission line. And also it gives for a transmission line. And for the transmission line, it gives that A is cosine beta, and we found D, all right, or D we will find. So it's beta D. Then B is J0, Z0, Z0, sine beta D. C is Jy0, sine beta D. And D is cosine beta D. And since you know your frequency, which is beta, how much is beta? 2 pi over lambda. You know your D, which is in lambda, all right? And how are we going to find D? D is the distance. We found it is 0.094 lambda, where D, so it's times 0.094 lambda. So practically, if this 2 pi is 360, 0.094 times 360 gives me 360 times 0.094, 33. That's about, so times D, obviously. It's about 33.84 degrees. And the cosine of that gives me 0.83. B is J50, the sine of that, so 33.84 sine, 0.55. C gives J 1/50, and sine, which is the same, times 0.55, and D is the same thing like A, 0.83. So practically, we have 0.83 J and 50 times 0.55 is 27.5. This one is it was 0.55 divided by 50. And this one is 0.83. And that's the ABCD matrix for 2. And then what do we do to find the total ABCD matrix? We multiply the two matrices. So 1 minus J 8, 5, 0, and 1 by 0.83, J 27.5, J 0, 1, 1, and 0.83. And then you find your ABCD. This is for 1, this is for 2. All right? And your ABCD matrix is going to be complex. It's going to have, for example, the first one, if you do the multiplications, all right, you're going to find a matrix that's going to have A, B, C, and D. Okay, then from that, you are done with the first problem. If I want you to find the Z matrix of that, practically you will have to find the ABCD and then change it to the Z matrix. or you will have to find the Z matrix. That's what I would do. I would find the ABCD and then from there find the Z matrix. All right. And then from the Z matrix, I would find the equivalent circuit, which would be for the whole circuit like this. It would be symmetric, obviously. And it will be Z11 minus Z12. Well, not exactly sure. I don't know whether Z11 and Z22 are the same, but in any case, Z22 minus Z12 and Z12. And that's the equivalent circuit for that. So practically, you will find, now, this equivalent circuit, what we know, and if you did not, later on, all right, when you have more experience, immediately you would say that I know that the equivalent circuit for a transmission line is like this. Where the values of L and C will have to be determined from here. All right, that's how a transmission line is. And they will be identical for the transmission line. And then I put a capacitance here. So practically, if you were to avoid the ABCD and you remember that the transmission line has this L symmetric, L on its side and then C, and if you could find those from the ABCD matrix, or you had them in a different way, found them, then practically your equivalent circuit is here. And this will be a different one, of course, C1. So you have 2 inductors, 2 capacitors. And you don't know exactly how that works until, because you have multiple elements, until you operate. What I would do, if anybody wanted me to find how that performs, I would assume that I excite it here with a voltage, and I will look at the voltage out. That will be the best way to find out how that operates, whether it has resonances. It has resonances, we know that, all right, because it has 2 inductors and it has 2 capacitors. Even if the inductors are identical, the way they are, you cannot sum them up because they are on opposite sides of the capacitor. So you know that there will be multiple resonances, but because there are multiple, you don't know how that's going to operate overall. So the best way for this is to look at V out. So you look at V out over Vs, and this is going to give you information about how this operates, especially if you were to plot it over frequency. All right, if you were to plot over frequency, you will find a performance on how that operates. You could find something like this. That's a bandpass. You could find something like this. You don't know because here it's at low frequencies, obviously. This is not going to pass through very much. Like at high frequencies, it's not going to pass through. So you know that both low and high will go like that, but you don't know what's going to happen in between. All right, you don't know whether this is going to be like this. You don't know whether it's going to be like this or whether it's going to have a much stronger resonance. You practically will have to find out exactly how that works.
For the purpose of classifying this behavior, you would say it's a bandpass because of we know that the low frequencies and high frequencies are down, right? Or they don't.
Yeah, but you don't know exactly how it looks.
Yeah.
It may be a very poor, all right?
So
because
for plotting these in terms of the circuit, are we allowed to use multisim Like
yes, you could. I mean, of course, I'm not going to ask you in the exam to do this.
Okay.
The reason I'm doing all of this is like any of the steps I can ask you, I will split a big problem and I will probably ask you one step to do in the exam.
Sure.
See, I'm not going to ask you to do all of this, obviously. No way. But now we are solving a problem just to make sure you understand the steps. And then I may ask you a small step, all right? I may give you an ABCD and say find Z. Or I may give you an ABCD and say find the equivalent circuit. See what I'm saying? Yeah.
And then for from what you were saying before, the transmission line equivalent, like where it's an L, and a C. Assuming that we're just taking the transmission line without cascading with anything else, it'll always give an L, and a C.
Yes.
Have any real components? Okay. Cool.
Yes, always, unless you include losses in the transmission line, and then it's going to give you some small resistors and a small. So if the transmission line has losses, it's going to look like this.
Yeah. Okay. Yeah, I remember that.
Yeah. It's going to be always symmetric, but it's going to look like that. And that's going to be a conductance. That's going to be a resistor. Small values for R and G. All right, in the most general case.
Professor?
Yes.
So if you were to ask us to like sketch the equivalent circuit, if you gave us the, I guess, the impedance matrix.
I could even give you the impedance matrix, exactly.
If you asked us to sketch that, you're asking for the sketch similar like the one you show on the bottom, but just without the inductance and the...
No, that is in the book. If you look at the page...
No, I'm saying you want us to sketch the one with just inductors and capacitors, not
yes.
one with the transmission line and a capacitor.
Usually always equivalent circuits, when we talk about an equivalent circuit, we talk about RLC. Always.
Okay. Yeah, that answers my question.
Yeah, always. And usually the way it comes out is if I give you Z, so let's assume I give you Z. The way it comes out is like this. From Z, you can always find an equivalent circuit. So this is Z11 minus Z12, Z22 minus Z12, and Z12. And for passive devices, that's for passive components, always looks like this. And so your Z11 minus Z12 is going to have a real and an imaginary part. The Z22 minus Z12 is going to have a real and an imaginary part. They may be the same or they may be different depending on the circuit. And Z12 is going to have a real and an imaginary part, but the best way to show it will be a real and imaginary. But the best way to show it is in terms of 1Z12, all right, which is going to be the Y12, which is going to have a real plus an imaginary part, okay? And that will be the best way because any real part and the Z impedances can be a resistor in series with an inductor, all right? Another resistor, another inductor. Let me see those. So that will be R1. What did I do? Oh. That would have been R1, L1. That move this further. Copy. That would have been an R2 here. R2. L2. And then here you would have G12 and a capacitor. So that's what you would find in the most general case.
A quick question about that.
Yes.
So for the parallel or the middle branch, we're modeling the resistive part as a conductance, but we're not inverting the capacitance. It's still an impedance rather than like a susceptance, right?
Yes, we keep it like that because they are in parallel and they're better to, we always shunt elements, we show them like this. Most of the time.
But that C12
yes.
is still C12. It's not 1 over C12, right?
No, C12 is C12.
Okay, thank you.
Yeah, these are, yes, exactly. Any questions on that? What other topics? This is the kind of type of problem I had defined for today. And the one that I have is similar, but it does not exactly has the same values, but it has all the data, the values. I did them all calculations and I will put them. So here, the one that I had created for today was this one. No, where was that? Did I do that? There. So I have done a similar problem, but I did all the calculations. And in this problem, I asked you a number of questions, all right? It's the same kind of that matching network. But so I'm not gonna ask the whole thing, but I can ask you one question, see? Like B. I can ask you a question like C. D. E, for example. So that's how, I mean, and I'm not suggesting will be those, but you may see a question like this.
So is the test going to be like one big question with kind of like you pick like 3 of these parts that you'd have us do or something like that? Or is it going to be like?
So I have to design it so if you make a mistake in one, those mistakes do not propagate. It's going to be easier for you. At the same time, there's going to be some coherency. All right, so I will not bring you totally different problem because it's easier to focus on one and solve different tasks, but also it has to have minimum. And I'm not suggesting, it's an optimization problem. I'm not suggesting you can always have minimum dependence between the questions. I would prefer to have one problem of one general category because then you can focus on that as opposed to having one from here, one from there, another. And then try, if possible, to minimize the dependence of one question on the other. But even if there is some dependence, usually if you make one mistake in one question and you use a different number, you're not going to be penalized twice. See what I'm saying? But I'm trying, whenever possible, I'm trying to limit that dependence. Any other questions?
I had a question about Smith charts that was brought up on Sunday in the review session on Sunday. So I remember you saying that like whenever you have any type of shunt, you always go toward the load, like to measure the length of that shunt.
Yes. Go ahead. Could you repeat again? I'm sorry.
Yeah. So I was just confused because like I've seen like in other resources they say go toward the generator. So
yes.
like the way
when you go So there are both ways you can go. You can start from gamma in, you see it here, gamma in.
Right.
And then you move towards the load, or you start from the load and you move towards the gamma in. Both are fine because what they ask you to do is to create a matching network that takes you from one to another. You know both of them. You know both your 100 ohms, and then you know your Z in has to be the complex conjugate. All right?
Right. So say for this question,
yeah,
we need a shunts at the load ends. Like say we want to have like an open circuited shunts. Like I'm not saying we do, but just like in other questions, they've been like that. So is the proper way to measure the length of that shunts to go from where the shunt is like open circuited, so like at the real line, and you go from that line toward the generator to the shunt value that you want? I know, I realize it's kind of confusing when I'm just.
So I'm trying to think on what your how to respond to your question. So let's take this one, all right?
Yeah.
In this one, let me see how I have it. You will see it in the solution. So ZL2 is this one, the red point here. This point there.
Right.
Oh, sorry. Here, let me do that. Okay, this point here
is the
load.
Right.
This one, there is the load. This one is gamma in. In this particular case, it happens that you don't need, I mean, just by a section of line, you can do it, see, without a stub. It just happened. I did it for a reason. Just
right.
to simplify things. So you can move, since you're at the load, you can move towards the generator. All right, practically it's like moving like this. Like this, all right, moving like this. If you go from here, or let me write, if you start moving from the 100 ohms to the front, which is from the red point to the blue, it's like moving towards the generator. So you will always be able to move like this. All right. But if I start at the gamma in or Z in, which is the blue point, and then I have to move towards the generator, then I will move like that. Towards the load, I will move like this.
Right, I understand just for a transmission line, and like you said, in this example, no shunt is required.
Yes.
I guess I had a question on when shunts are required.
No, you
like,
always, when a shunt is required, like in the one we did, let me go to, where did I go? No. Okay, too many notes for today, just a second. Did I erase my notes from today? No, these are the notes I had prepared and are there. But what happened?
Talking about the notes from Sunday's session, or
no, from just today. I don't seem to find. Just the ones that I was writing on. It's a recording anyways. I can pick this map from the recording. So yeah, so let's assume, let's go to this one. if there is in the notes today that I did, or let me just go to these ones that they have the Smith chart on. Let me go here, right? So let's assume that I have 2 points. The load, let's assume that the load is the red one here, okay? And I wanna go from the load, I'll put another point, this point here. And let's assume that I have to go to this point. Okay. Usually, as you can tell, going around the Smith chart is going along a transmission line is not gonna do it, because as you can tell, it's they don't have the same distance from the center. So if I were to write the constant VS, yeah, all right.
They're not on the same VSWR.
Exactly. If I were to write this one here, so it would be this, assumingly, and this one there, it would be that, but of course I would have to change it, put it like this, down.
You're saying the pink is the load and the green is the input?
Yes.
Okay.
Let's see. Let's assume it's that one, right, for simplicity. So 2 VSWR circles, they're not identical. So I have to do 2 things. If I start from the load, which is the pink dot, with the transmission line, I have to move along the transmission line. But I will move until when?
The real part's 0.4, right?
Was that?
Until the real part is along the pink VSWR is 0.4?
Yes, until, exactly. But which it cannot go to 0.4 though.
Okay, yeah, I see.
So so if I move along this, I will never cross the 0.4. Okay. So practically, I will move along this until I go to 1. No, I have to go to this point. I'm sorry, this one. I will then start with a green point, and I will have to do a number of things, all right? So obviously it's not gonna be easy the way I did it. So if I go through the green point, which one should I go through? The 0.4 is the one that is here. I cannot cross it from the pink circle, but
so along the green, would you go until you intersect where R equals 2?
Yes. Okay. So the best way to do it, unless I'm gonna include many more elements, all right? So because I can still show you how you can go from the pink, but I would have to include more elements than just 2, than a transmission line. But from the green, yes. So you go from the green, and the green is on the source side. So I will go from the green towards the load, okay? So from the green, I have to move along this until I find the 2 point. So I will have to move around, come here. All right? And then from there, so I go from like that. And then from there, I go down like this. When I move along the green, I add a section of a line. When I move along the pink, I add the reactance. So when I move along a section, so practically what I'm doing here is, this is my load, my source, I meant to say. And this is the input reflection coefficient that I need, All right, so that's point, what I'm gonna call A, and the other is point B, say. And my load is here, and this is point B. B prime, and this is point A prime. And now I have to add something in between. What I see is that as I move from the generator towards the load, which is the green line, so I add a section of a transmission line here, whose length I will have to find from this distance I'm traveling. All right, and we'll talk about it. And then when you arrive to point C, which is this, then I add a reactance to move from point C to B. So practically, yeah, here I'm
the value would be -3J, right?
Yes.
Cool.
The value is going to be negative, so it's a capacitor. In fact, you add a capacitor because it's negative, so you have to add an inductor, excuse me. All right, you have to add something positive.
Right. So to cancel it out, right?
Yes, right. So that's what you do. Now, there was, yes.
So instead of the inductor, if you want to do a shunt or a say like an open circuited stub.
A series or a shunt?
A parallel, so shunt.
Parallel, then in that case, you will work with admittances. So in that case, to work with admittances, see what I'm gonna do. I'm gonna erase this. I'll keep this VSWR circles, but instead of B, I will go to point. I will move my B point to a anti-diametric opposite, which is here. And that's going to be the admittance at B. See? And then instead of point A, which is which is my impedance, I will move to also the I will draw the diameter, and then I will move to this point. And that's now it's going to be my admittance at A. All right?
Right.
Now, I will have to move from A towards the load. So now I'm moving different distances. I'm going to move like this. Let me see. But now, yes, okay. So the load at this point has a reactance. I'm going very close, so practically that's why I got confused a little bit. But let me erase that. So you see the B now, the admittance is going somewhere here. There is, if I take this point, which is called, it's the reactance of the admittance. All of the points have the same resistive part. I mean, have the real part of the admittance. So I'm gonna move from point A until I arrive to this one point. Okay. You see that? So I'm gonna move from A towards the load until I get there. And then I'm gonna move down until I get there. So the yellow is gonna give me the distance. The pink is gonna give me the reactance, but they are all shunt. I mean, the line is line, obviously, but the reactance is shunt that I will get from A prime to B. See that?
Right.
Also, the section of the line changes. It makes sense. The length of the transmission line changes. And how you find the length of the transmission line is you have already one line here. You extend that. You need another line to go to A prime from the center. Let me see. There, you need another line that goes from here. Ah, what line is that? Goes from here.
And right, this is the length of the transmission line.
Yes.
Gotcha.
The length of the transmission line is from here. How is the length of the transmission line? In transmission line, this is the beginning at the end. Yeah, so it goes from here like that. All right, and you find the length from the points you read. And then from A prime to B, which practically is from here, there, you find the distance on the stub. Yes, the same thing from the, yeah.
Okay, okay, gotcha. Yeah, I think in 322 and like other sources, I learned you go clockwise or you go toward the generator, like from that
always
open circuited admittance lines. The stub.
So whether it's open circuited here or short, it's up to you, because not always an open circuited or a short. So here, for example, if I look for the shortest distance, all right, because I could either stop there, the blue line, or I could go all the way around and stop here. All right?
Right.
For admittances, this is open. This one is open for admittances.
Right.
And this is short. So if I want to have an open stub, I would rather have an open because it's short. All right. And if I want to have an open stub, I stop there. If I have a choice, I will go always for the shortest length.
Gotcha.
Yeah.
Cool. Yeah. Thank you for explaining that.
Yeah. Now that we design matching networks, especially for amplifiers, how you move from which point, it may change. You want to feel comfortable moving one way or another, but it's always the same, you know? I mean, the movements are the same. It's just that you go left or you go right. You always go right or you always go left. When you're on a stub, you always go towards the load. All right? On a stub, you always go towards the load.
From the stub line to the open or shorts.
Yes. And then you select open or short depending on your constraints. If you are free to do whatever, I would always go for the lowest length. The lowest length may get me to a short, or the lowest length may get me to an open. But if I have microstrip, and I know that I can only do an open and a short is out of the question in my design, that I will go to an open no matter what. It might be long, and then in that case, if people come back and say, this is huge, you know, we cannot manage it in our layout, then you will have to go back and think of a different type of an arrangement. There are multiple solutions, obviously, using the Smith chart. There's not only one single. I mean, we already thought about two solutions here.
Gotcha, gotcha. All right, yes, thank you.
Sure.
Can I clarify one thing?
Yes.
So just trying to get general intuition of the Smith chart here. But,
yes.
So when you're on so in this at this stage, we're flipped to sort of the admittance version of our Smith chart.
Yes.
Right. And in this case, when you follow the constant resistance line counterclockwise, you're adding like sorry, I'm losing my train of thought, but that's that's adding a negative reactance. So that's adding a capacitive shift.
Always when you go, whether you are, so let me say, whether you are on admittance or impedance, specific things are identical. So when you move along a concentric circle like here, like the red and the pink and the green, you are always moving along a transmission line.
Right.
Always. Now, which direction you go along the circle, there are two possible directions. Moving counterclockwise or clockwise. Which of the two you will select depends on where you start and where do you go. If, for example, you start at point A prime and you want to go towards B, then you have to go towards the load. If you start at B, from the B point on your Smith chart, and you want to go towards A, you have to go towards the generator. That tells you which direction to go. Counterclockwise is towards the load. But you don't have to memorize that because it's written, all right? You should not memorize anything practically. Try to remember that it's written here, which direction to take. Then from there, the moment, so you always, when you start moving on the Smith chart, then the next point is to intersect with the real part of the load you are getting to. All right, so when I was moving from A, I was looking and I was moving towards the load. All right, so I was moving in that direction towards the load. I was trying to find where is the circle of the real part of my admittance. My admittance was at B. The circle of the real part of my admittance was this one. Okay? The one that I don't know whether that shows well, but this one.
Yeah, that makes sense.
And yes, and I tried to cross it there, which is in fact somewhere here. And then from there I go down and I find my point B. And as soon as I do that, then I start measuring distances. All right? The distance for the line, which is the yellow. The distance for the stub, which is the pink.
I have a question about that.
Yeah.
So when you take the distance for the line, it's from A to A prime.
Yes.
But when we take in the length of a stub, are we supposed to find the complex conjugate of A prime and then?
No, if it's shunt, no, you stay with admittances all the way. Because if it's shunt, you add. When you move from point A prime to B, and practically you are, I called it A prime. Let me see, I should probably call it something else. Let me call it, so we are not getting confused. Let me call that point, say C, all right? And that's somewhere, point C, it would be somewhere here. And from C now, you have to move down to B. So you measure the line. Now you have to measure, so C, the point C has a positive reactance, susceptance. These are admittances, all right? Point C has a positive susceptance. So to go down to B that has 0, it implies that my stub, you remember it's a sound stub, so let me erase this here. My stub now, this one. My stub looks like the, not this one. My stub looks like this now. All right, and that's why. And that happens to be a susceptance. Okay. Now, this B, the susceptance, I found that when I arrive at C, that's my C point. At C, the impedance here, the impedance that I see here as I move towards the load at C has a normalized part of point, let me see, I don't see very well, 0.4, 0.6, 0.4, 0.5, 0.6. Okay, 0.5 say this is about normalized, all right? Is about 0.58. And of course, that's it, 0.58. That is, oh, no, C I said, plus J, you see, C, 0.58 plus J of 1.7. That's point C. Now, to go to point B, which in fact tells me that at this point, I need to see only a 0.58, all right? That's my point B. Then at that point, I have to go from 0.58 plus J17 to 0.8, or in fact, since I'm looking towards the load, all right, I'm looking like that. So my Y input normalized at C is Y, which is here, plus YL. Do you agree?
Yes.
All right, this is YL. So practically, I know my Y in C, which is 0.58 plus J17, and I know my YL 0.58. So that tells me the Y has to be J 1.7. So I found that the Y that I need to add there to be able to see my load after, or to be, you know, to see my load after I go past Y, because now since I'm looking that way towards the load, I have to sum Y and YL to see Y in, all right? I have to sum them. And that's what gives me this Y to be 1.7. So practically, to be able to find the length of the stub, then I need to go from, I need to find a stub that gives me 1.7, and then 1.7 goes up here in the blue line. If the stub is open, practically, all right, my reactance from 1.7 would go, this is open. So it's going to give me that as length. And why is that? Because when the stub is open, this is your stub, open. And you have that length here we found, say, LS. Now, your input admittance to the stub is J Y naught tangent of beta ds, which is identical as if we were to say that. All right? So practically, an infinite, a zero admittance for an open stub gives me the same impact like a an impedance of a short stub. Got it?
Yes.
So the short for impedance is the open for admittance. That's the only thing you need to remember if you go from impedances to admittances. And then you find the length. It just needs a little bit of practice, but it's always the same. Always the same. Now, if your colleague, as your colleague said, if you can do this using other means, you know, different than the Smith chart, and you feel comfortable like using MATLAB, you know, I will be good with that, as long as you do it accurately. But if you don't have access to MATLAB, right, at that point, or if you're like me, that I don't know MATLAB that well to use it with fluency, then I would say I would use what you know best in that regard. The only thing about the Smith chart is that MATLAB does not allow you, you have to tell MATLAB how you're going to do your design. The Smith chart gives you all the possible designs you can do. You identify your architecture, if you like, from the Smith chart, as opposed, so it's a true design tool, as archaic as it seems, you know, it's an amazingly interesting design tool. And I don't know why somebody has not developed an easier way to use the Smith chart on the computer. It's kind of very weird that people, maybe because people are just going directly to MATLAB, they try a few things and that's why. Any other questions?
None here. I feel pretty good about the Smith chart stuff. I think this was helpful.
Yeah, okay. I will put my solutions. They're similar problems, but not identical. Very similar, but not identical. I will upload those for today, from the office hours. I will make them available now.
Sounds good.
Can you also please upload the solution for homework 4 and 5?
Yes, I will do that. Absolutely.
Thank you so much.
In fact, I expect the TA to do the 4 and I will finish the 5 and submit it tonight. Let me need Chaui.
Yeah, I'm here.
Yes. Hi, Chaui, could you send me solutions for homework 4?
Let me see. Homework 4.
Unless you send them to me and I did not see them.
Okay, can I send you tonight?
Yes, send it and I will do the other one so we can upload them.
Okay.
Yeah, that would be great.
Because I'm sorry, because I haven't finished my own report yet.
Okay. Yes, we will need to do that because the students take the midterm on Wednesday.
Okay.
Thank you.
Okay. Oh, they'll have the midterm on Wednesday.
Yes. Exactly.
So okay, then I think I should send you the solution for homework 4 tonight, and I'll find some problems for the matching network and the transmission line. And do you?
Okay.
Are
No,
you going
I don't think I need those, but it will be nice to have them for later in the semester for some more.
Okay.
Yeah.
Yeah, I was going to finish the solution of homework for on Saturday, but I didn't expect that the report is so time consuming.
Which report?
My
okay.
my own class, the machine learning by Professor
got it.
Kumar.
Okay. I know. We are all in there.
It's a 5 pages report and a lot of math problems.
Oh, okay. Yes, well, do the best you can because we will need, I will finish the homework 5, and if you can finish homework 4, that helps.
Yeah, thank you for understanding. I have spent all my weekends on this report.
No, I understand. Well, I know. That's the part of the semester that everything is like, there's tremendous pressure, attention.
Yeah.
Okay, that's where I think we are. So if there are any questions you guys have, you can send me on group me, but I check it out not too late because I'm also trying to focus on some work that I have to do myself. And or any questions, if you have additional questions about the midterm, just send them to me and I will try to respond. Okay? See you all on Wednesday. Take care.
Professor, could we speak in a breakout room for a second?
Oh yeah, let me see. How do I take you to the breakup room?
Can we pause for a second?
How do I do that?
Maybe you can give me the host and I can set the break room for them.
Yeah, but he needs to speak with me, the student.
Yeah, I'll set you and him in the same room.
So how do you set this up so I know?
I think at the bottom you can set.
There's a breakup room.
Yeah, there's a
says assign 5 participants now.
You can just assign yourself and the students.
Okay.
And leave all of the rest of us in the lobby, and that's fine.
So I create a break room, but then assign what? Assign the people.
Yeah, you can just assign
yeah.
yourself.
What's your name? Who Bradley? Do you want to?
From Managing Kumar.
Yes. Sorry, it's one. Yes. Okay. And then Linda. All right. So I did. And then what do we do next? Oh, there we are. Do we do anything else?
No, you can just leave rest of us in the lobby.
How do you put the rest of you in the lobby? So
you do nothing, then we are in the lobby. We will in the lobby.
Can you hear when I speak with Rohit?
No.
We're not in the breakout room yet.
You're not. How do we go to the breakout room? That's what I'm asking.
I'm not sure on that. I've never done that.
You need to set.
There we go.
I'll join. Okay.
Cool. You're muted.